molar volume at STP. So scientists use STP as an abbreviation for standard temperature and pressure. So when we say STP, very concisely, we're saying we mean this particular pressure and this particular temperature. Standard pressure is 1 atmosphere, or 760 torr. Standard temperature, 273 Kelvin, or 0 degrees Celsius. It should be 273.15, but close enough. Why did they pick these particular pressure and temperature? Because they're easy to establish. So remember, all this gas law stuff was done before the discovery of electricity. There's no technology, right? They didn't have ovens with thermostats to control the temperature or refrigeration to cool your reaction mixture, right? So if you're trying to do a gas experiment and you want to know what the temperature is, the easiest temperature to use is 0 degrees Celsius, because that's the temperature of an ice water bath. It's the melting point of water. So if you put your reaction flask, submerge it inside a big bath with ice and water, wait a few minutes, you can be confident without even measuring the temperature that it's at 0 degrees Celsius. And so that's very easy to establish. Standard pressure is 1 atmosphere. That's normal atmospheric pressure. Also very easy to establish. You can put a manometer on your contraption and just adjust it so the levels on each side are equal, and then you know the pressure inside equals the pressure outside. So 1 atmosphere, 0 degrees Celsius. STP is useful for making comparisons between gases, because when we talk about gases, we've got 4 variables. When we talk about solids, we're talking about pretty much just the mass of it or the volume of it. One or the other, doesn't matter. We're talking about solutions. We've got the concentration, the volume, that's it. But gases are kind of squirrely. So STP is useful. We've talked about atomic mass and molar mass. Atomic mass is the mass of an atom. A molecular mass is the mass of a molecule. Molar mass is the mass of a mole. Molar volume is the volume of 1 mole of gas. We have to specify temperature and pressure, so we say at STP. So this is a value that will be given to you on an exam, but let's calculate it just because that's what the slide says we should do. So we want to find the volume of 1 mole of gas at STP. So starting with the ideal gas law, I'm trying to calculate volume. So I'm going to rearrange this. I'm going to divide both sides by P. I'm going to end up with the volume is equal to N times R times T over P. So the volume of 1 mole. How many moles of gas do I have? 1. Yeah, don't write with the highlighter. It doesn't work very well. And we're considering this 1 mole to be exact. R, same old R, 0.08206 liter atmospheres per mole Kelvin. Some calculators actually have that constant built into your calculator, so you don't even have to type it in. You can just recall it. That's not cheating. What's the temperature? It would be 273 or 273.15, depending on how picky you're going to be. So I'm feeling picky today, so 273.15 Kelvin. Standard temperature, 0 Celsius, or the equivalent in Kelvin. What's the pressure? 1 atm. That's standard pressure. So my units are going to cancel out. I'm going to end up with 0.08206 times 273.15. So the volume here would be 22.414689. Is the ideal gas constant an exact number? No, it isn't. It could be written with more significant digits, but 4 is plenty for most purposes. So this is what's going to limit the sig figs here, liters. So as we calculated it here, we're going to get 22.41 liters, the volume of 1 mole of gas. 1 mole of what kind of gas? Any gas. It's kind of weird. It's usually rounded to 22.4 liters per mole, I think, because the next digit's a 1 and it doesn't matter that much. It's a little sloppy. The molar volume of any gas at STP is 22.4 liters per mole. Doesn't matter what the gas is. So a mole is 6.022 times 10 to the 23rd molecules or atoms of gas. It's a number of particles. The identity of the gas doesn't matter. The volume occupied by that many particles will be the same regardless of how large the individual particles are. Will these 22.4 liters of gas have different masses? Yes, they will, but their volumes will be the same. I talked to you about Wyoming, right? And gases? No? Okay. What the heck? So my parents live in Minnesota, and we've made several cross-country trips, and sometimes we go through Wyoming. The population of Wyoming is about the same as the population of Fresno without Clovis. The whole state, right? It's beautiful, but it's largely empty. So you drive through Wyoming at night, and you can go for miles and not even see a light from a ranch. I mean, there's just like no civilization evident at all. Lots and lots of space. So I think of Wyoming as being like a gas. There is so much space between the people that how big the people are doesn't matter. So what would be maybe a liquid or a solid version of people might be people in an elevator. So I think the elevator in this building says it can hold 10 people, something like that. So think about a small elevator, 10 people in there. Does the size of the people matter now? Yeah. If you have 10 kindergartners or 10 defensive linemen in there who each weigh 300 pounds, you're going to have a different experience, right? Those big guys are just going to cram in there and barely fit. That's what happens with liquids and solids. The particles are touching really close. The size of the particles matters. In the state of Wyoming, would it matter if all of those people were teeny tiny little elves or enormous giants? Wouldn't matter. There's so much empty space between them that the size of the people doesn't matter at all. That's the way gases are. So that's Wyoming. So this is a very useful conversion factor for gases. Only works at STP. Here's a picture. So we have 3 balloons here. The volume of each is 22.4 liters. At STP with helium, that would be 1 mole of helium. STP for xenon, 1 mole. STP with methane, 1 mole. Would these balloons have the same mass? No, they would not. How much would this helium balloon weigh? 1 mole of helium. 4.003 grams. How about the xenon? 131.3 grams. They're taking up the same amount of space, but this one weighs a heck of a lot more because each of the particles is heavier. These particles are also larger than the helium particles, but there's so much empty space in between them that the difference in size doesn't matter. It's a little hard to get your mind around. So then we can ask conceptual questions like this. Assuming ideal behavior, which of these gas samples has the greatest volume at STP? So what are we even thinking about here? Greater volume means more particles, right? So larger volume means more particles. Some of them are atoms, some of them are molecules. Right? Because more particles will take up more space. The mass doesn't matter, but here we have 3 samples. They're equal in mass. Do they have the same number of particles? No. If we converted a gram of hydrogen to moles, we'd use its molar mass. That would be 2. For oxygen, it would be 32. And for argon, it would be about 40. So the argon atoms weigh more than the hydrogen molecules. So in the same mass, which one of these is going to have more particles? The hydrogen. The one with the smaller, lighter particles. The same amount of mass. So it's a little bit like saying, well, I've got a pound of grapes. I won't spell it correctly. Pound of grapes, a pound of apples, and a pound of grapefruit. Individual pieces of fruit, which one's going to have more pieces? The grapes, right? Because you can actually have an apple that weighs a pound, or a couple apples. But have you ever seen a 1-pound grape? I haven't. Not even those big globe grapes. They're not a pound. So that's the idea here. Any questions? Because the mass of a sample of gas at STP is going to be different, the density is going to be different. So the volume at STP of 1 mole, always 22.4 liters. But the mass of that sample is going to be different, and the density of the sample is going to be different. So one way to find the density of a gas at STP is you can take its molar mass and divide by its molar volume. That works just fine, provided you remember the equation. I prefer to stick with just a few equations and create what I need. So I'm going to do it without using this. So calculate the densities of helium and nitrogen gas at STP. So I'm going to think to myself, well, what's density? Density is the mass divided by the volume. Does the density change if I have a lot of gas or a little bit of gas? Density does not depend on how much stuff you have. Density is an intensive property. It doesn't depend on how much there is. Pardon me? But for a single substance, the density is not proportional to the volume. The mass is proportional to the volume, but the density is constant. The number of particles is different. So densities for gases are a little different to think about than densities for liquids and solids. But the density is the mass of the sample divided by the volume of the sample. One of the tricky things, with a problem like this is they didn't give me a sample size. What do? I make something up. I decide. I get to decide what the sample size is. I can choose something that's easy. I think that 1 mole would be easy. So I'm going to choose to do this calculation with 1 mole of gas. I've already been told it's at STP. So what's the volume of 1 mole at STP? 22.4 liters. What's the mass of the gas? Depends on the identity, right? So helium gas. What's the mass of the helium gas? 1 mole of it? 4.003 grams. So then the density for helium is the mass of this sample size that I picked, 4.003 grams, divided by the volume, 22.4 liters. And that would have 3 sig figs. I'm going to be sloppy and just round it off right now. So that's the density of helium at STP. Densities of gases are usually given in grams per liter because they are so much less dense than liquids and solids. I also want the density of nitrogen. Is nitrogen a diatomic element? It is, and so it's N2. Helium is not, and so we just use He, but nitrogen is one of those 7 that we have to remember, and so the mass of 1 mole is 28.02 grams. So the density for nitrogen, the mass is different, 28.02 grams. What's the volume of 1 mole at STP? It's still 22.4. .25 grams per liter for nitrogen. The nitrogen gas is more dense than the helium because in the same volume you have the same number of particles, but the particles are significantly heavier, like 7 times heavier. Any questions? We ended up doing this, the molar mass divided by the molar volume. The molar mass, 4.003 grams divided by the molar volume. But I came at it in a different way that involved just thinking about it instead of memorizing an equation. If we want to calculate the gas density with under other conditions other than STP, then we again need the mass of the gas and the volume of the gas. And so what the book is doing here is they're taking the basic density equation and they're saying, well, the volume of a gas could be found using the ideal gas law. Sorry. It was just air. He bumped the little air valve and then, yeah, blew the paper towels all over the place. It's awesome.
I thought I was about to explode or something.
No.
I was like, hold on, we gotta evacuate.
No, we're fine. So you can calculate the volume using the ideal gas law. Volume is nRT over P, and stick that in and rearrange things and get this equation. The density of a gas is the pressure times the molar mass divided by R divided by T. That equation is valid, but you have to remember it. We can also use the same approach that we used in the previous example. The density is the mass over the volume. Let's pick a sample size, calculate the mass, calculate the volume, put them into the density equation. I prefer this because there's fewer equations to remember. So if you want to use that equation from the book, you're welcome to do that, but I'm not going to do it in lecture. Calculate the density of xenon gas at a pressure of 742 millimeters of mercury and a temperature of 45 degrees Celsius. So when I see this problem, calculate the density. My mind immediately goes to what is density? Density is the mass divided by the volume. So I need the mass of a sample of gas and I need its volume. I was given a pressure and a temperature. So let's write that down. The pressure is 742 millimeters of mercury. The temperature is 45 degrees Celsius. The density is the same regardless of if I have a small sample of the gas under these conditions or a large sample. So I need to choose what volume I want. 1 mole, almost always the best choice. So again, I'm going to choose 1 mole of gas. And then I'm going to calculate the mass of 1 mole, which is easy, and the volume of 1 mole, which is a little more involved, but still not too hard. So xenon gas, what's the mass of 1 mole? 131.3, right? I need 3. I read that straight off the periodic table. 1 mole of xenon weighs 131.3 grams. Now I need the volume. Well, how do I calculate the volume of a gas? Ideal gas law. So I rearrange the ideal gas law and I get volume equals nRT over P. So I need the amount of gas in moles. Oh, I chose that, it's 1. I need R, I need the temperature in Kelvin, and I need the pressure in atmospheres. So I've got pressure in millimeters of mercury, I've got temperature in Celsius, but I can fix that, right? Okay, this is the day of writing the equations in the wrong place. So just move that out of the way. Converting from millimeters of mercury to atmospheres. 1 atmosphere, 760 millimeters of mercury. The most common mistake students make with that is they switch them and say 760 atmospheres is 1 millimeter of mercury. Well, stop and think about that for a second. Regular atmospheric pressure, 1 atmosphere, just like the name suggests. 760 atmospheres would be 760 times regular pressure. That's ginormous. And that would cause a column of mercury to go up 1 millimeter. That's not right. So switch it back. It's an atmosphere of 760. So 742 divided by 760. Three sig figs in my pressure. There's 3 significant figures. Carry 2 extras to avoid rounding errors. If you round it to the correct number of significant figures, your answer is going to be close enough. But if you round this to 1, then you might be in trouble. So if you're not sure how many significant figures to keep more than you think. So 45 plus 273.15, 318.15 is the temperature in Kelvin. And that's going to have uncertainty in the ones place. So my temperature went from 2 sig figs to 3 sig figs. That happens. I'm going to plug things in. I picked 1 mole, 0.08206 liter atmospheres per mole Kelvin. See, now darn it. Technical difficulties. It's cheating, I know. 318.15 Kelvin. Divided by the pressure. So I've got 1 times 0.08206 times 318.15 divided by 0.97631 equals 26.740 liters. That's the volume of 1 mole of this gas under these conditions. So I plug the volume in over here. (131.3) divided by 26.740. It's just poor planning overall on this slide. 4.9102 grams per liter. 4.91 grams per liter. Questions?
So instead of going through that long process to find the volume, why didn't you just use 1 mole at STP is 24 point?
I can't use that here because it's not at STP.
Yes, but then you find the volume by cross multiplying, because this is giving you 742 millimeters, so 760.
I see what you're talking about. I don't necessarily know that that would be simpler. It depends on how you think about things. If it makes more sense to you, essentially you're making a simple gas law problem out of it, where the temperature and the pressure are changing.
Right, well, the volume we already know is 22.4 at 760 mm, so 742 is plus
So volume 1, we could call 22.4. Pressure 1 is 1 atmosphere.
No, 760, we could definitely also be getting 760.
Okay, yeah, we could do it that way. And temperature. (318.15 Kelvin). And we want volume 2 and pressure 2 is 742 millimeters of mercury, and temperature 2 is 273.15 Kelvin. And we want V2. So I could derive an equation by dividing one ideal gas law by the other. The n's and the r's are going to cancel out. And so then I can plug these numbers in and find out what V is. And it's an entirely valid method. It's going to make a lot of sense to some people and not much sense at all to other people. Okay? Any other questions? You should get the same answer though. 4.91 grams per liter. The density of a gas is 1.43 grams per liter at a temperature of 23 degrees Celsius and a pressure of 0.789 atmospheres. Calculate the molar mass of the gas. So you could use the equation that the book gives. And if you have the equation in front of you, that's probably the simplest way. But if you don't have the equation, what do? Well, what's molar mass? It's the mass in grams divided by the number of moles, right? Does the molar mass change if I have a small sample or a large sample of gas? No, it's the same. So again, they're not giving me a sample size, which means I get to pick the sample size. What do you think I'm going to pick? 1 mole. I'm going to choose to do my calculations for 1 mole of this gas. So I'm given the density 1.43 grams per liter. I'm given the temperature and the pressure. Could I find the volume of this gas? PV equals nRT. If I divide by P, that's a shaky P on both sides. I picked N to be 1 mole. I know what R is. I was given the temperature and the pressure. One mole of gas, 0.08206 liter atmospheres per mole Kelvin. What temperature should I put in there? Should I put 23? No, I can't put 23 because Celsius doesn't work. 23 plus 273.15. What's the pressure? 0.789 atmospheres. Why was 6 afraid of 7? Because 7, 8, 9. There's a Yoda version too, but I always mess it up, so I'm not going to do it.
I haven't heard this since like elementary school.
I don't. 7, 8, 9 comes up a couple of times in my lecture slides because it's examples in the textbook, and I just cannot help myself. I have to say it. So it's 0.08206 times 296.15 divided by 0.79.
I have a question.
Mm-hmm.
So you only have to convert to like atoms and Kelvin when you're using the R constant, but if you're doing like simple gas laws and they give you milliliters and milliliters, you just do the as milliliters, you don't have to
Right.
do the conversion?
So when you're using the ideal gas constant, and it's easy to mistake ATMs for atoms, it's atmospheres.
Oh, atoms.
Very similar. When we're using the ideal gas constant, we have to use the units in the ideal gas constant. In the simple gas laws, where we're looking at essentially ratios of things, As long as the units are the same, they will cancel out. The one exception is temperature.
So it
Has to be Kelvin, and it has to be Kelvin because unlike milliliters or atmospheres, the pressure, my brain is melting. The temperature conversion is not just multiplication. So the conversion factor won't cancel out. It involves adding. So I get this 30.801 liters. How do I find the mass of that? I was given the density, 1.43 grams per liter. This is a conversion factor. I've got liters. I'm going to multiply by grams, divide by liters, 1.43 grams. I still have that 30.8 in my calculator. I'm going to multiply by 1.43, 44.045 grams. So up here, for my molar mass, I picked 1 mole. So I found the mass of 1 mole, 44.045 grams is 1 mole of this gas. That is my molar mass right there. So instead of remembering a new equation, I used Pivnert, the ideal gas law, and I used the definition of molar mass, which I know, and I used density as a conversion factor. Those are all things that we've done before. Any questions? Conceptual problem. Arrange the following gases in order of increasing density at STP. This is the sort of problem that students often get wrong on an exam, and there's multiple reasons for getting it wrong. One is that you don't understand the concept behind it. Another is you don't understand what the question is asking you to do. So we want in order of increasing. So that means we start with the smallest thing and we go to the biggest thing in order. So we're going to start with the smallest density to the largest density. And I can tell when a student misunderstood the question because they have the answer exactly backwards. So density at STP. At STP, 1 mole of each of these gases occupies the same volume. But the mass will be different, right? So I'm thinking, well, density is grams over liters. And if I imagine 1 mole of each of these gases, their volumes will all be the same. So the only thing that's changing is the mass. So to have a large density, I need a large mass. So what I'm looking for here is the smallest density will be the lightest, the smallest molar mass, and the largest density will be the heaviest, the biggest molar mass. So probably instead of trying to order this in your head, writing down a couple of notes. So 35, this is where you can just kind of round numbers. So chlorine, 35 roughly, so that's going to be about 70 for 1 mole. Fluorine, 19, so that's about 38. Oxygen is 16, it's O2, so that's 32. Neon is what? 20. So the smallest density will be which element? Neon. And the largest will be chlorine. And then from neon, who's the next largest? Oxygen, and then fluorine. So neon is smaller than oxygen, which is smaller than fluorine, which is smaller than chlorine. This was about 20, 32, 38, and 70. So without examining these choices, I wrote down what I think is the correct answer. And then I'm going to compare this to these letter choices and pick the one that matches. Right? So that's going to be A, right? Multiple choice problems are sometimes easier because you've got some hints, you've got just things to pick from, right? But sometimes they're more difficult because looking at all those choices can be confusing. So sometimes it's best to just cover up all the choices, answer the question as if it was an open-ended solve this problem question, and then look at the choices. Any questions? So the molar mass of an unknown volatile liquid can be determined experimentally, and this is what we're going to do on Thursday in lab. So you can take a sample of the gas and heat it. A sample of the liquid. If we know the mass of the sample, we heat it so it becomes a gas, we can measure the temperature, the pressure, and the volume of the gas. Pressure, temperature, and volume allows us to calculate the moles of the gas using the ideal gas law. So moles, we're getting that from the ideal gas law. N is equal to P, that's not a P, PV over RT. And the mass is just measured. So we measure the mass, we calculate the moles from measured volume, pressure, and temperature. We take the mass and divide by the number of moles, so we can get the molar mass of the liquid. Because the molar mass of that substance doesn't change when it becomes a gas. So here's an example. A sample of a gas has a mass of 827 milligrams. Its volume is 0.270 liters at a temperature of 88 degrees Celsius and a pressure of 975 millimeters of mercury. Find its molar mass. Sometimes we abbreviate molar mass as mm. So that's the mass in grams divided by the moles. So here, the sample size is specified. We're given its mass, its volume, and its temperature and pressure. Did they give me the mass in grams? No, they didn't. They gave me the mass in milligrams. Darn them. Well, we can use our knowledge of the metric system. Milli means 10 to the minus 3. Or 827, and instead of milli, I'm going to write times 10 to the minus 3 grams, which you can use like that, or if you put it into decimal notation, it's the same, 0.827 grams. So that's the mass of this sample, 0.827 grams. And now I need to find how many moles of gas. PV equals nRT. This time I'm looking for N. So I divide by RT, on both sides. R's and T's cancel out over here. So N is equal to PV over RT. What's the pressure? 975 millimeters of mercury. Do I have the gas constant in my equation? I do. It's down here. That means I have to use particular units. Millimeters of mercury doesn't work with the ideal gas constant. 975 millimeters of mercury. Need to convert that to atmospheres. 1 atmosphere, 760. So it's 1.2828 atmospheres. So pressure, 1.2828 atmospheres. What's the volume? 0.270 liters. Does that unit work with the ideal gas constant? Yes. Here's the ideal gas constant down here, 0.08206 liters times atmospheres divided by moles times kelvins. And I need the temperature. Temperature has to be in kelvins. 88 degrees C plus 273.15. $361.15. When I look at my units, atmospheres cancel, kelvins cancel, liters cancel. What I'm left with in the units is no unit in the numerator and 1 over moles in the denominator. That is the same as moles. You can believe me or you can understand fractions, I don't care. So my units are okay because I'm trying to find how many moles. When you do this on your calculator, you need to be very careful because what your human brain sees is this number times this number divided by this number times this number. If you say that to your calculator, it's going to misunderstand you. So let me see if I can make up an example. Let's say I have 2 times 3 divided by 2 times 3. Do that on your calculator. If I type it in as I'm reading it, 2 times 3 divided by 2 times 3, my calculator says 9. Is that equal to 9? No, it's equal to 1. What happened? Well, what your calculator understood was 2 times 3 divided by 2 times 3. So that's not going to get us the correct answer. What I prefer to do is I see this as being the same as 2 divided by 2 times 3 divided by 3. And so 2 divided by 2 times 3 divided by 3. Students don't tend to like that. So 2 times 3 divided by parentheses 2 times 3. Now what do you get? Do it. You get 1? okay? Anytime you have two numbers in the denominator, you need to watch out for this, because it's a shame to do all of this work correctly and end up with the wrong answer because you had a misunderstanding with your calculator. Someone's calling me. I'm going to ignore them. So, punch this through on your calculator and make sure that we get the same answer. I'm getting 0.011687 moles. Anybody else get that? So that's the amount in moles. I'm going to put that into my molar mass calculation up here. So I've got 0.827 divided by 0.011687 equals so I'd round this to 70.8 grams per mole. Anybody else come up with that? Got 70.9. That's still reasonable. If we get a little bit of difference in the last significant figure, those numbers are still considered to be the same. Is that a reasonable molar mass? Is it a possible molar mass? Yeah. What's the smallest possible molar mass? 1.008, really, because that's the mass of a mole of hydrogen atoms. Can we have anything that's smaller than that? Not that's an element. I mean, you could have a mole of protons, but yeah, good luck getting those in a dish. So your molar mass should be larger than 1. If you end up with something smaller than 1, your calculation is wrong. Go back and check your work. We also shouldn't end up with something in the millions, right? Molecules can have molar masses that large. DNA is a molecule, and a mole of DNA actually weighs a lot. But would you be able to make it into a gas under these conditions? No. Yeah, so the book got 70.7. Call that good. Okay, this is another example of finding the molar mass of a gas. This one is more like what we'll be doing in lab on Wednesday. So an organic chemist isolates a colorless liquid from a petroleum sample. She places the liquid in a pre-weighed flask and puts the flask in boiling water, which vaporizes the liquid and fills the flask. She closes the flask and re-weighs it. Her data is given below. Calculate the molar mass of the liquid. So what I have here is the volume of the flask, which is the volume of the gas. I have the temperature of the water bath that the flask was in. And if it's in there long enough, I can assume that the temperature inside the flask is the same as the water around it. So I don't actually have to measure inside the flask. Much easier. The pressure, this pressure is actually just whatever the barometer says is the pressure in the room that day. Because as she heats this, it's open to the atmosphere. The pressure inside the flask is equal to the pressure outside. So she heats it up until it's all vaporized, and then she caps it off so that it can't escape and so nothing else can get in there, and then she weighs it. Does It's a slightly different procedure than we'll be doing, but the calculation is very much the same. So she has the mass of the empty flask and the mass of the flask with the gas in it. So to find the molar mass, we need the grams of this sample divided by the moles of the sample. How do we find the mass of the gas? We subtract, right? 78.416 grams minus 77.834 grams. Use your calculator. See, that's where we're different from math class. I don't care if you know what the names of the different things are, as long as you can do the calculations. And just go ahead and use your calculator. So that's the mass of the gas. We don't want to include the mass of the flask in our molar mass, right? Because that's not part of the gas. That was just the container. So we have our mass, 0.582 grams, and then we need to calculate the moles. Ideal gas law. We rearrange the ideal gas law, we go N equals PV over RT. Ideal gas constant tells us what units we have to use. Liters, atmospheres, and kelvins. None of them are right. How many liters is 213 milliliters? 0.213. If you have a good grasp of the size of a liter and the size of a milliliter, which if you stop and think about it, how big is a liter? It's half of a 2-liter soda bottle. Can you visualize that? How big is a milliliter? Can you visualize the 10 milliliter graduated cylinder? And 1 milliliter is this much in there, right? So if I have 213 milliliters, do I have 213,000 liters? No. That's the common mistake, is you divide or multiply wrong. You make it the wrong, you move the decimal point in the wrong direction. Or you can just be super safe and 1 times 10 to the minus 3 liters per 1 milliliter. 0.213 liters. 100.0 degrees Celsius. We need that in kelvins. Since this is got uncertainty in the tenths place, I definitely would want to use the 0.15 here. So this is going to be 373.15 Kelvin. And then the torr is the same as millimeters of mercury. So 1 atmosphere is 760 torr. In an example like this, where you have just a regular flask, and especially one that's open to the atmosphere, your pressure in atmospheres should come out very close to 1 atmosphere. It's not going to be exactly 1 because atmospheric pressure fluctuates and we are not at sea level. We're really close, 300 feet, but still not sea level. Okay, so I've got all of those, and now I can calculate what N is. Pressure, and the volume, divided by R, and the temperature. Get your calculator out and do the calculation to make sure that your calculator is cooperating. It's not your problem, right? It's the calculator's problem. If you need me to come over and, knock it upside the head, I can do that for you. Anybody else get that? It's always a good idea to do the calculation twice. Same thing. If you accidentally multiplied the whole thing by 373, you end up with a really large number of moles. At STP, which is not that different from regular atmospheric pressure, a mole of gas is 22.9 liters. That's a cube about this big, like kind of a nice packing box. So if I have a 213 milliliter flask, can I have hundreds of moles of gas in there? No. It should be a small number. So I'm going to put that number in up here. So 0.582 divided by 0.0069011. .334, which would be 84.3 grams per mole. That's the molar mass. Is that a reasonable number? Yeah. Now, if you calculate your moles wrong, let's see if I can do that. I'm trying to take a shortcut, and it's not a good idea. Okay, 0.9921 times 0.313 times 0.08206 times 373.15. I end up with 9.5 moles, which doesn't seem like a horrible number. But if I plug 9.5 moles into my equation up there, 0.582 divided by 9.5, I get a molar mass of 0.06. Is that possible? No. Nothing can have a molar mass less than 1, which is the smallest element. So getting a molar mass in your answer that's smaller than 1 is a clue that something's wrong in your calculation. Oh, I guess I didn't have the answer on that one. Any questions?